All right, what's up everybody? Welcome back to Structure Free Learning. And in this video, we're going to do a example problem for 1D motion with the case of constant acceleration. And in this problem, we have a car that's moving with a speed of 20 meters per second when it starts decelerating at a rate of 3 meters per second squared. And because the acceleration is a constant, this is a case where we can use our constant acceleration equations to answer these questions. You'll notice the car is moving to the right. Its velocity is in this direction of motion. The acceleration, because it's decelerating, is opposing the direction of motion. So it's slowing it down. Instant where my car begins to decelerate is essentially my beginning. And I'll call this right here, this point right here will represent t0, and I'll measure time from that instant there when I start pushing on the brakes, essentially. All right. And this would be my initial position. I'll call that 0. And this 20 meters per second is actually an initial velocity, v0. Like this. All right. And what we want to find in this problem is we want to determine the velocity of the car at 3 seconds. And we also want to know how long does it take for the car to stop, and what is the displacement of the car when it stops. So whenever we work on a problem, we might have a problem statement, but we really want to kind of highlight the important aspects or things that we understand from the problem statement. And so here we're given time is going to start the instant we hit the brake or we start to decelerate. So here we'll say t0 is 0. Our initial velocity is 20 meters per second, and we have a constant acceleration of 3 meters per second squared, and it would be negative because it's opposing the direction of motion. And what we want to find in this case is we want to find the velocity at 3 seconds. We want to know the time when this velocity equals 0, and then we would like to know the change in position or this final displacement of the car when the velocity is 0. All right, so let's go ahead and get to it. To answer the first part, so we need the velocity with respect to time. And we know that when we have constant acceleration, you don't have to memorize these equations. You could actually evaluate the integral, but over time, usually, the more you practice it, you'll get a sense of it. Our t0 is 0, so our velocity as a function of time is equal to v0 plus act. And in this case, our initial velocity is 20 meters per second minus 3 meters per second squared times t. And my velocity evaluated at t equals 3 seconds, I just got to plug and chug, is 11 meters per second. And this would be the answer to that first question. What is my velocity at 3 seconds? And then if I wanted to find the time when the velocity or when the car stops, I can use this relationship again. And here, this relationship is this v is v0 plus act, and when the car stops, the final velocity is 0. And so the way that my relationship would look would be 0 is equal to 20 meters per second minus 3 meters per second squared times t. And t is my unknown in this case, and when I solve for t, I would get 6.67 seconds. And this is how long it would take for the car to stop. Next, I want to find the change in position with respect to time. And this can be done in 2 ways. And the first way that I can answer this question is that because I know the time it takes to stop, I can use my position function here for constant acceleration, which is this s of t, or position with respect to time, is this s0 plus v0 t plus 1/2 act squared. And I know the time it takes to stop. The change in position would be s minus s0 is equal to v0 t plus 1/2 act squared. So this change in position is equal to 20 meters per second times 6.67 seconds minus 1/2 times 3 meters per second squared times 6.67 seconds squared, like this. And this will tell me that this change in position is equal to 66.67 meters. So that's one way to do it. The other way to do it is, if you don't know the time, we have constant acceleration, you know the initial velocity, and you know that the final velocity, we want to know the change in position when v equals 0. This relationship here, we have this popular v squared minus v naught squared is 2ac times s minus s naught. And this term right here is just the change in position, like this. And so if I want to solve for the change in position, I know that the final velocity is 0. The initial velocity is, I do know that already, it's 20 meters per second. And I know the acceleration is -3 meters per second squared. And so I could just go ahead and solve for delta s, which would be 0 squared minus 20 meters per second squared divided by 2 times -3 meters per second squared. And this will give me that the change in position is also 66.67 meters. And really what I found is, if I go back to this drawing, is that the time at which this particle stops, or this car stops, this velocity equals 0 at this instant, at 6.67 seconds, v equals 0, and my position is 66.67 meters. Because we started at 0 here, this change from here to here, this change in position, is 66.67 meters. This is kind of an introductory example to 1D motion. The only way that this thing can really get complicated is if you had like two particles and then you want to know when they might meet or when they might collide, or what their relative distance is between these two particles experiencing constant acceleration. Another way to make this difficult would be to have various phases of motion, like a portion where you would be accelerating and then you hold the gas pedal so it's experiencing constant acceleration, and then you release the gas pedal so that there is no acceleration. So it's the hard part might be keeping track of the phases associated with the particle's motion. All right, so hopefully this was useful. Take it easy. Structure free.